So for this sharing, I'm going to share how to leveraging OLAP for our real-time analytics. For today's agenda, I will share some of the usage scenarios in real-time analytics, and also there are a few technical solutions in the market on cloud and also on-premise solutions. I will discuss some of the architecture and the solutions, benefit and pinpoint with you guys, and then I will do some sharing about future direction. To know that this is just my assumption for the future directions. If you have any other opinions, feel free to share. And then I will give some minutes for Q&A. So for usage scenarios, I think one of the most typical scenarios we can imagine for real-time analytics is the sales performance streaming dashboard. So you can link it as your double 11 or double some campaign time of the real-time dashboard, which you can get insight from this kind of dashboard. There are a few typical characteristics of this dashboard, which is it only shows the most critical indicators, and also it will force you to only focus on the indicators which are really important, because in one dashboard, it only contains very few metrics. And also these indicators are in streaming and are time series, which means these metrics are keep changing by the time, and you have to get it in real time to take actions immediately. Otherwise, some of the you will lose some cost. And also, it will enable this kind of streaming dashboard will enable IT department and business to take actions more quickly. So as some of the statistics show that it will improve the time to decision about 2.5 times greater than those who don't use the streaming dashboard. So that means it will keep your business more faster and take actions more frequently. And also another typical scenarios is fraud detection. So this one, as you can share, like especially like the chart I share in above, is like a credit card detection. So that means it can, based on the streaming technology, it can detect your fraud in real time, and then to take actions in real time, even though visualized as a dashboard. And also you directly pause the transaction. So this kind of things can help you have some benefit, like immediately response and also minimize the downtime. And also it will keep monitoring the transaction online, and then to take actions immediately. So some of the organizations implement this kind of prevention measures experience a loss that 55%. So these are some of the typical scenarios. I think there are a lot of other scenarios, especially like in machine learning model, you have real-time features, and also in the logistic domain, you have last mile streaming dashboard to help you to improve the performance. I think there are a lot of scenarios in there, but it's not say like streaming will cover everything, will eat the batch, but it's just like it will empower the data in streaming perspective, and it will unlock a lot of critical scenarios for customer and for your business. So I think that's the scenarios part. And regarding for the technical solutions, I think it have been involved multiple times. So in the first stage, I would say it's more like a Lambda architecture. So from this chart, it can be Spark streaming and a Flink, or Flink can be data processing, and Kafka as a data streaming, data storage, and HBase or other KV store as the data storage for serving. So from the left side, I think this one, I also use this architecture three to 4 years ago. I think it's very stable and typical in I think already also even now in most of the companies. For the from the left side, the data will be synced into the speed layer as well as batch layer. So by using the streaming ingestion, it will be synced into the Kafka, which means like you capture your CDC or directly send the log to Kafka, which is streaming storage. And then it will be processing by some processing engine like Flink and Spark streaming. For Spark streaming, it will micro batch processing it batch by batch, but for Flink, it will be event based. So, and then after processing, it will go into a streaming view, which is a serving layer. You put your data inside of the HBase or ClickHouse or other NoSQL database like MongoDB or even the MySQL. And then for your streaming dashboard, you can frequently consume the data from the serving database, or you can build a WebSocket to continuously to monitor the change and display the data in real time in your dashboard. So this could be the typical solutions under Lambda architecture. And in the meantime, you have a lot of batch requirement as well, which you need to calculate your historical metrics. So you put your data in Hive. Recently, there are data lake solutions you put in Iceberg, and also anything as a batch storage, or even you put inside of your object storage as a batch storage, and you plus a batch processing engine. Maybe in cloud you have Asana, or you have, and in on-premise you maintain a Spark, or you maintain a Flink batch, or yeah, and then after clean up and processing, join, aggregation, this kind of thing, you will put your batch data periodically, maybe hourly, daily, or weekly into a serving layer. And then in your dashboard, you can query it. You can query your batch data, and then you can display into your dashboard, or you can analyzers can directly query the table in there. So this kind of architecture typically solve most of the problems of when the business want to get insight from the data. But there are also some of the disadvantages or cons, like the metrics in the batch layer and the metrics in the speeding layer is not exactly match, because for the data for the speeding layer you calculate recent data, but this data is not in batch layer yet. And also in the speed layer, the order is not guaranteed, because the Kafka cannot guarantee topic level sequence. It only partition level sequence. So it totally depends on the data when you upload it into Kafka, the sequence you upload into Kafka. If the sequence is different, then your metrics display in your dashboard will be slightly different with your batch. That means it will cause confusion for some business, and also maintain this architecture is a big effort. Need a lot of data engineers to do it. So this kind of thing keep evolving. So a lot of people are going to think like, are we able to merge this batch layer and a streaming layer? And in the first time there is a Kappa architecture, but I would say it's a very temporary architecture, because use Kafka plus streaming processing engine to purely solve batch and streaming data needs. It's not that realistic. So, but then after recent years, we have a data lake solution. So so that means it can solve most of the, it can be a production ready solution. So can solve a lot of problems. I think this one, but there are also some pain points for this solution. But let me share what this kind of a technical solution and how it can solve our streaming requirement. The conditions in here is like not all the requirement need in real time, which means in milliseconds or seconds level latency. Most of the requirement can accept a minutes level or tens of seconds level latency. So based on this kind of thing, we are using recently there is an Iceberg or Hudi or data lake, which created by Databricks, and then they can support the like minutes level pipeline. So from left side, your data will still be going to Kafka as a hub, and then where you can use the Flink CDC. directly from RDS or from Kafka, and then you can landing your data into storage, which you can be HDFS S3. And based on that one, you have Iceberg, which is an open format to support the processing of this, support the data storage, which is using a table format. And then based on that one, you can use Flink or Spark to processing the format. Then then continuously to consuming the data from the layer by layer, and then can clean the data, and then can combine it as a data warehouse. And then all the data inside of the Iceberg table format. Fundamentally, it's still object storage or a distributed file system. But in the upper layer, they have a format layer to let the processing engine. The processing engine can be multiple. I use the Flink as the example, but there are a lot of processing engine can integrate with Iceberg. It's a very open format. So the benefit of this one is like when from layer to layer in the data warehouse, it can be very frequently compared to previously batch job, which we are trying to load data from layer by layer. Normally it's hourly or daily, but this one can be minutes level or sub minute level. So and then the data from the after going to the DWS layer, and then it can fit into a data serving storage, and then the analytics and the dashboard can directly query this storage to get the insight. So I think there are a few benefits in there. The first one is we don't need to maintain a very complex batch and streaming architecture separately, and then this one will dramatically reduce the metric difference when we are using the data. And secondly, it will reduce a lot of the effort to maintain the different big data technologies, tech stack. There are a huge amount of tech stack you needed to feed for the Lambda architecture. But in this one, what we need is only very few. We reduce a lot of dependencies. And also compared to using Kafka as the storage in the Lambda architecture, in here you use Iceberg, you can directly use Presto, or directly use Flink to query the data inside of Iceberg. So because Kafka is a sequence, the data is coming in sequence, and it's storage in log. It's not able to support you directly do the analytics based on Kafka. So in here, you can have this benefit to directly query the Iceberg table, and then to get the result immediately, or to do the data discovery. So this is, but there are also some cons for this architecture. The first one is the data is not coming to our data warehouse in real time, real time, which means in second level. And also in server layer, you still need to maintain clinicals, HBase, and Elasticsearch, this kind of data serving, which is an OLAP engine. So it still have a way to go, like how we can simplify this architecture at the meantime, and how we can make our data more reduce the latency of the data. So that's I would say this is an upgraded version of Kappa architecture. Okay, so and then another solution, I think it's on cloud. This one is compared to the our on-premise or our own data. We own our infra ourselves, the architecture. This one is a cloud architecture. So for cloud, there are a lot of solutions like Databricks. Databricks is similar like to the previous one, Flink plus Iceberg, because data lake is similar to Iceberg. So the solution is very similar to this one. But for the Snowflake, it have another solution. So it use a Snowpipe service, and then to periodically loading into a Snowflake database. But for this solution, I would say it's not a pure streaming solution, and it have a latency. because from the architecture you can see, like when you want to load some data from your source files in source database to Snowflake, for example, MySQL, you have to periodically dump your data into S3, and then you send a RESTful call to the Snowpipe service, and then Snowpipe service understand and will periodically continuously load the data from S3 bucket, which is your staging arrow in Snowflake context, and then into the Snowflake database. I think it's quite promising and stable in this architecture, but it's like micro batch way. So you have to continuously write the data into S3 and then load into Snowflake. It increases a lot of latency, but the benefit of this architecture is it's not that complex. It don't have a lot of dependencies. So if you don't have a very higher requirement on the latency, maybe you can have a try. So for these are the current typical solutions which in the market offer. Maybe in other cloud like BigQuery, like Azure, they have similar architecture. Yeah, I won't share all of them. So the rest are some of the thoughts that are from my perspective, which may be some of the future directions for the streaming analytics and the data infra to support the streaming analytics. So I think it should be, the first one should be compute and storage segregation, which means, for example, in the Kafka scenario, if your data volume increasing, you have to increase the capacity of the Kafka. It will cause some resharding. So it will cause the shutdown in some edge cases of your Kafka cluster. And Iceberg is a more makes sense because the data, the storage is put in Iceberg, and also the compute can be scaling if you are using Flink or Spark. So in the future, it will be a compute and storage segregation architecture to match the processing. And the second one is a vectorized computing engine. This one is why it's this one, because even for Databricks, they have a new Phantom engine to support in the future, more and more customers require lower latency when query the data. So this one will be much powerful compared to like purely using Flink or Spark processing to do the processing the data and get the analytics. This one will cause some latency when you query the data, especially when you have a very complex query. And it should be cloud native and also SaaS and multi-tenant, which this one will be open out-of-box features because a lot of customers don't have a very large investment on the data engineer team. So they may need a out-of-box product which can support them to run the business and bootstrap the business as soon as possible, and also get the data insight as soon as possible. So this will be a very important feature. And also in the meantime, consider about the security as well as because especially for some startups, they are growing as well. So the resource usage and the cost will be also continuously growing together with the company growing. So that means this kind of a platform should be support the resource scalability and isolation. So I think so that's why my thought is that's why we are building a ByteDance product to fit this kind of requirement to allow the customers very easily to use data warehouse as well as build data insight for our from the data. So this kind of architecture is like you can directly streaming integration of your source data like your RDS change log, Kafka, and also your incremental logs. And then you use the streaming integration engine like Flink CTC or our ByteDance provided materialized MySQL to load the data into ByteDance first, which is ELT. So you load the data first and continuously loading. And then the data after landing into ByteDance, it can be architecture by different layer by layer. and then in each layer it will be scheduled by the DBT or Airflow. So which means you can purely architecture your data warehouse inside of ByteDance, and also you can directly query the data from the inside of the ByteDance table. So this will simply very largely reduce the complexities of your data warehouse architecture and make you easily to get insight from the data. And also we are SaaS application, cloud data warehouse SaaS, as well as we provide the scalability of the virtual warehouse resources, and we are also storage and computer segregated to match your requirements. So this one means you can start with a very small resource, buy a very small resource in ByteDance, and then if your company's data volume keep increasing, you can keep increasing your resource. So it will can be quite fit your business need. Okay, so I will try to share a quick demo. So how to do this one? Let me switch my screen. Okay. So for example, I created a database in MySQL, and then there is a table which is a customer table, and also I have created a materialized MySQL inside of the ByteDance, and then when I query it, there is no data in there. But then so that means I'm trying to synchronize the data from my MySQL in real time into our ByteDance, and then beyond that you can architecture your data. So this one should be an ODS layer, and then inside of the MySQL part, I can insert like a few of the customer data, and in here I can see that the data is already been synced in here. So this is so your whole database will be directly mirrored to the ByteDance, and then based on this one you can create table, create different layer, and then you can serve it. So then you can do a very easy query. You can see like you can analyze each region. There are how many customers there, and then for example the data keep coming from the source. This one is mock, keep coming from the source. So you can see, for example, you have an application, you keep coming from the source, and then the data will be periodically sync into ByteDance as a ODS layer, and then when you try to query, it will be in real time. That means all the source data of your MySQL will be in real time to sync into our database, and based on that one, sync to ByteDance, and based on that one, you can architecture your data warehouse. Okay, I think that's just a very quick demo. Yeah, so this one will be quite fit to the architecture. Means from the left side you have a RDS changelog, which is a customer table. I have created a materialized MySQL DB, and then it will keep continuously syncing to the ODS table or inside of ByteDance under my tenant. And under my tenant, I only use a very small VW resource. And then based on that one, after syncing here, you can create your DWD table, and then you can create your ADS table, and then you can run query directly. So this one will be in real time. Yeah, I think that's all for my sharing. So I saw there are 2 questions. From dashboard perspective, what is the threshold to be set? Is Lambda architecture from dashboard perspective, what is the threshold to be set for consumer? Actually, this one from dashboard perspective, we are also most of the real case is periodically to query the data as well, like 30 seconds to 1 minute. And then when you try to consume it from the batch to batch to increase the throughput, because if every record you are going to process it and consume and process it, it will be cost a lot of resource. So normally it will be our practice is 1,000 to 5,000 based on the latency you can accept, as well as the how many resources you are using to process. Second question, in Kafka, I see you are using Kafka to store CDC log manual. Why do we need use MQ? Can we directly dump the logs into HDFS? I think yes, we can directly dump the log into HDFS. But using Kafka Kafka support change log. So if you directly dump into HDFS, that means you switch to like a batch layer. So why I use the Kafka as the in here is to emphasize, to highlight that this one is for the streaming layer, which is a speed layer, which is a streaming processing. You can dump into HDFS and then do the batch processing based on that one. Okay. Okay, I think that's all for my sharing. So if you want to get a white paper for ByteHouse, you can scan the QR code here. I think that's all for my sharing.